So the next topic that we will cover is the validity of the lumped capacitance method. So we just mentioned three key parameters that influence the approximation to the lump capacitance. These were thermal conductivity, convectivity transfer coefficient, and the size. And there is a dimensionless number that contains all these three parameters. It's called BO number. So it is indicated by BI. It's a BO number. So it indicates the ratio of heat convection to heat conduction. Conduction is with H, convection is with conduction is with K, convection is with H. So now if you want to visualize this, so initially you have an object that is at T initial Ti, and then you submerge it in a fluid which has convection coefficient of H, temperature of T infinity. If you wait infinitely long, this object is going to be T infinity everywhere, okay? Okay? So the lumped capacitance method is valid if the BO number is less than 0.1, okay? So this is the criteria that we are going to use in this course. So if the BO number is less than 0.1, so then we can approximate the system is behaving as a lump. So that means temperature is only a function of time. And if the BO number is not smaller than 0.1, then the temperature will be function of position and time. That means we cannot use the lumped capacitance method. Okay? So as a side note, this criteria is, as you can see here, it is basically a heuristical number. Some textbooks use, instead of 0.1, some textbook use as 1. So in some other textbooks, okay? Some other textbooks use this 1 as the criteria for the lumped capacitance method. But in this class, since I refer you to using the book by Incropera et al., so let's stick to the notation that if the BO number is less than 0.1, we will use the lumped capacitance method. If it is not, we have to use another method, so we will talk about it later. So now let's focus on this BO number some more. So what is LC here? LC means the characteristic length. How do you calculate that? So the characteristic length is defined as volume of the object divided by the surface area of the object. Again, in this case, the surface area is the area which is in contact with convection. So this is in contact with convection. So if you have some areas that is not in contact with a fluid that is resulting in convection, you don't count that area. You only count the area which is contributing to the convective heating or cooling in the system, okay? So now if you use this formula, if you apply the formula for a sphere, you know how to calculate the volume of a sphere and you know how to calculate the surface area of the sphere. You take the ratio, you'll see that this critical number or critical length is the radius over 3. And if you have a long cylinder, so that means we are neglecting the caps in convection. So that means the length is very large. L is much greater than diameter or radius. If this is the case, so the critical length is R0 over 2. Okay? So you can simply calculate this if you want. So let's say this is length L and this has radius R. So what is the volume of the cylinder? Pi R squared times L. And what is the surface area of the cylinder? 2 pi R L. And again, we are not adding the caps. We are calculating the only area, side area. So if you take the ratio of these, pi's will cancel, L's will cancel, and R squared will become R. You'll be getting R over 2. And if you have a short cylinder, so you have to consider for short cylinder, so we have to consider the A cap. So surface area is basically 2 pi RL plus, we have two caps, two sides, pi r squared. This will be the area. Okay, so this is for the surface area for the short cylinder. This term is the surface area for the long cylinder. And if you have a heat plane which is asymmetric, let's say T1, T2, if the temperature on two sides are different, and then in this case, let's say in this case the characteristic length is simply this length L, okay, if it is asymmetric. If it is symmetric, so if two sides are at the same temperature, we know the temperature profile could be linear, so like this, or symmetric, so it could be a parabola like this. So in this case, so we'll be using L over 2 as the L over 2 as the critical length. Okay, this is a small nuance that we must pay attention. So if the boundary condition is asymmetric, so temperature 1 is different from temperature 2, we'll be using the full length for calculating the critical length. But if it's a symmetric situation, both sides are at the same temperature, then we'll be using half. This is just the convention for this type of analysis. Alright, so now let's talk about, now we understand under what conditions we can use the lumped capacitance analysis and under what conditions we cannot use the lumped capacitance method. Now let's see, how do we analyze this? So basically, what is the advantage of this method? Let's do an actual analysis. Let's say we have an object which is initially at temperature Ti, and the temperature is uniform everywhere. And let's assume that in this system, the lumped capacitance method is valid and temperature is only a function of time. It is not a function of position. Okay? It's only a function of time. It is not a function of position. So now let's say initially this temperature is Ti, and we submerge it in a liquid which is at temperature T infinity, and T infinity is smaller than Ti, so this is a cold fluid, and we have a hot object. We submerge it in there, and we would like to know how does the temperature changes with time. How do we calculate this? So we will be simply doing an energy balance here. So we will select our object as the control volume. This is the control volume. So what is the energy balance here? So we have this control volume. So we have energy in minus energy out plus energy generation is equal to rate of energy accumulation. So in this case, this was initially hot. So we had a cold fluid here, right? So what's going to happen? So we are doing an overall analysis for the whole object. So what are the terms that we need to consider? So there is no generation because there is no reaction within the object. There is no heat coming in because the fluid is cold, the object is losing heat. So we only have energy out, and that energy out is going to determine the rate of the change in the energy of the system. Okay? So now, how do we express the heat being taken out from the object? So we have the surface area. This is the surface area of the object. Let's call this as AS. This is the surface area. And T is the temperature of the object, and it is uniform everywhere. Again, we assume the temperature is a lump. It doesn't have any temperature variation. So T is the same everywhere, even on the surface. So that is T. And the fluid is at T infinity. So the temperature's difference between the object and fluid is delta T here. And if you multiply it by AS and multiply it by convective heat transfer coefficient, we calculate the rate of heat taken out from the system. And And what is going to happen? This heat is going to change the energy accumulation in the system. So this is basically MCP delta T. So if you want to think about it, MCP delta T is in thermodynamics. This is the internal energy of the system. And so we are interested in how it changes with time. So we take the time derivative. So instead of MCP, we write rho times V. This is the mass. So Cp is the heat capacity for solid. Again, Cp is equal to Cv for solids, roughly, for solids. Okay. So this is the internal energy coming from thermodynamical principles. So the change in internal energy should be balanced by the loss of energy due to convection. So that is our equation. So now let's take a look at this equation and see what kind of equation is this. So can we solve this equation? So let's take a look at here. So we have temperature. It's a function of time. So we have one variable. So this is an ordinary differential equation. And we can even make this equation even simpler. So if we substitute this term, if you refer to that as theta, theta is t minus t infinity. So that means if I take the derivative of d theta, that's equal to dt, because t infinity is constant. So if you take the derivative of both sides, this is the equality. That means d theta by d time is equal to dt by d time. And if I use this substitution here, so if I substitute this term in here, so the equation will become this. This we have equation in terms of theta now. So then you can separate the variables. You collect the time term on one side. So this can go here. Theta term on the other side. So we have theta and time. So now we can integrate both sides and integrate it from t0 initial to any arbitrary time t. And initially we have temperature initial, and at time t we have just temperature t. So, and if we want, since we are working in terms of theta, theta initial and theta at any time. So now if you take the integral of both sides, so we have minus t, so integral of this is minus t, and delta theta by delta theta by theta is going to give us log, and since we are integrating it from theta to theta I, so we have this expression. And I can rearrange this equation because I'm interested in change in temperature of the object with time. So I will rearrange this. I'm going to take the exponent of both sides, take exponent of the both sides. And if you take the exponent of both sides, so you will have, so basically, so you can combine these terms with t here, and you can take the exponent of both sides, and you can flip them around. So you can ln 1 over x is equal to minus ln x. So we are interested in finding theta. So if I take the reciprocal of this, so I need to multiply everything by -1. So that's why I'm getting a negative term here. And everything else here is combined. So we have theta over theta I is equal to exponential of the product of these terms. Okay? And if you want to write down explicitly theta in terms of temperature, we use our original substitution. Theta means t minus t infinity. Theta I is ti minus t infinity. And now we do have an expression. So this is the variable we want to know. Temperature of the temperature as a function of time could be calculated using this expression.